And then today, the lecture will be presented by ASML. And then our speakers today is Ronald Gusens. ASML, as you know, sorry, just leave the teams. Okay, so the ASML, is a leading company for EUV lithography equipment. And our speakers today has been with ASML for 20 years. And besides his position in the ASML, he is also adjunct professor at Purdue University under ECE. So without further ado, let's welcome Ronald.
Hey, hello everybody. First, let's check. Mic is loud enough? Everybody can hear me good? Awesome. Hey, it's always a pleasure. This is now, what is it, Sophie, the third, fourth, fifth time that I do this?
Countless.
Countless, right? And this is one of my most favorite events because I teach, and it's fun to teach to graduates, and it's fun to teach to seniors, but to see all the interest of first-year engineering students that come and to help share with you a little bit about my enthusiasm that I feel for the industry that I work in. So that's really a great pleasure. And I see that my slides are already up. Awesome. So we can get going. Come on. So this is quickly about me. I was born and raised in the Netherlands. I studied physics in the Netherlands. Fell in love during an astronomy course with computer modeling, in that case for stellar interiors and nucleosynthesis. And this was in the time that the whole university had one computer. And we used punch cards. But we were still able to, with a team of about 5 students over 9 months or so, to put a program together that we could actually simulate what is going on in stellar interiors and how does that lead to evolution of these stars. And for me, that was the beginning of a lifelong love affair with computer modeling and simulation of complex problems. And the last 20 years I've done that for imaging at the resolution limit, and that resolution limit has become smaller and smaller and smaller. When I started working in the semiconductor industry for Philips Research, you can see that was in the 1980s, I was working on 3-micron technology. And when I stopped working full-time for ASML 3 years ago, I was working on 1 and 2 nanometer technology. So I've had the privilege that in my own career, I've seen transistors get 1,000 times smaller on the same 1,000,000 times more transistors on the same surface area. And what that has done for our industry is amazing. So what I'm going to do today is I'm going to talk for a part, looking backwards at what has been going on in the history of Moore's Law. And then the second part of my presentation will all be about looking forward. What are some of the challenges that we have? Before I continue, I will show this again at the end. So if you don't, I'll give you all a few seconds to do this. And if you don't find your phone fast enough, it will show again at the end. But networking, I love it. So I will be back end of November and early December for 2 weeks on campus. I always love to hang out with students, so if you say, hey, I've got some questions and so on, just contact me, feel free to do that. Who knows what this is? Don't see a lot of takers, okay. This is actually Janus. He's the Roman god of religion and myth. And he was the god of the beginnings, of transitions. And he gave his name to the month of January, because with 2 faces he could look backwards and he can look forward. So I made him the moniker and for this presentation, because that's what we're going to do. So let's first look back at 50 years of innovation. And you've all heard about Moore's Law, and Moore's Law is about twice as much every transistors every 2 years. So for this presentation, I'm comparing it to the old story about the person that had helped the king, and the king said, ask for anything you want. And the person said, give me 1 kernel of rice on the first board, the first checker on a chessboard, and give me 2 on the next one, and 4 on the next one, and double it. Would you be willing to do that? Oh yeah, easy, thank you. Well, obviously that king was not very good at his math, because he very quickly ran out of rice. By the time that he gets to that 64th square, he will have to give about 9 times 10 to the 18th kernels of rice. Well, we're going to use this a little bit as an analogy for what happened with Moore's Law. And that first transistor was really in 1947. You can see it here on the left. There you go. First transistor, not fully integrated. And then here, a little while later, Kilby was able to create the first transistor. That was created ultimately with something like this. I have a wafer here with photoresist on it and a mask. The mask is the blueprint of the patterns that I want. And in a contact aligner, we would just shine light, and the shadow of the mask would expose the resist. And anywhere where the resist becomes exposed, it becomes soluble. Now I can remove the resist. Now I can use deposition processes or etch processes or ion implantation, and that's how you can build up a whole chip. If you look at the productivity that we had at that moment in time, a single thing was a square, let's say 40 pixels, and it took about 40 seconds. So at that time we were able to transfer from the mask to the wafer the equivalent of 1 pixel, 1 piece of information per second. And with that we were able to build stuff like this, transistor radios. Transistor radios in the 1950s were a really big deal, because it was no longer that a radio was that thing that was sitting in the living room. You could actually have something that you could carry. Oh my God, a radio that you can carry, right? You can also see that first computer from IBM. And you can see all the way on the right, the very famous, in my time, set of logic chips that Texas Instruments started to sell. And you can see here now that that had 4 inverters inside that one package. That was really exciting, because now you could build your own circuitry. 4 inverters. An inverter is a PMOS and an NMOS. That's 8 transistors. A little while later, we started to be able to do more. And here you can see on the left an example of how we used one-to-one printing. So there is a mask here. I shine the light through it. With this mirror, it gets reflected back and forth, and I now get an image of a slit of this mask on the wafer here. And I can scan both of them at the same time through the slit, because that's the part of the image that has really good quality, so that they would blend out where the optics was not good. They didn't know how to make a large field with good optics. And now they could do the exposure. And with that, we were able suddenly to do quite a bit more. So now we're already in 1973, and we were able to do, substantially more transistors. And this translated now, this one-to-one projection lithography. Here you see the numbers. There were 75 millimeter wafers back then. Now we use 300 millimeter wafers. That piece of equipment could do 40 wafers per hour. The latest ASML scanners can do 400 wafers per hour. And of course, in the meantime, the patterns have become much, much smaller. But at that time already, we were now able to transfer about 6 million, 5.8 million pieces of information every second by doing optical lithography. And this is what we were able to build with that in the 1970s. this beautiful portable phone. Now, I see all these iPhones, we've come a long way, huh? The battery in that thing, by the way, typically you had that as a sling separately hanging on your hips, because that took a lot of that. This famous Apple I computer, that was 1970. And the next step was, let's do reduction lithography. That way we can still have large patterns on the mask, but if we reduce now, we can fit more onto the wafer. And we scaled from 3-inch wafers to 4-inch wafers, 5-inch reduction lithography, and now we were able to transfer already 56 million pixels per second, 1984. With that, we, for the first time, were able to make a CD player. We had the first IBM personal computer. And we had the beginning of the 386, 486, 586 Pentium series of computers, chips that Intel made, all working with one and the same instruction set that got expanded more and more. Next step, let's use shorter wavelength, 4:1 exposure, step and expose, it was called. And if you take one of my classes in a few years from now, I teach nanolithography much more extensively. I'll tell you much more about it. But by this time now we're suddenly up to 3.1 billion pixels per second. We could now do half micron features on 200 millimeter wafers, 100 wafers. So we've gone from 1 transistor per second, or 1 pixel per second, to 3 billion pixels per second. Using that rice analogy, on this square of the chessboard, we have enough rice now to fill 5 trucks, each with 20 tons of rice. And I'm using that as an analogy because it's so easy to lose track of the incredible impact of this reduction in size that we've had. I remember during the very first of these changing the world with chips that Dave Janus did a few months ago, right? That he asked how many transistors here in the room. And remember that we all came up with 500 billion, 1 trillion. And the reality was you were off by a factor of 1,000. Right? The power of this miniaturization is incredible and continues. So now we finally were at the point that we could have really portable phones. Did any of you ever see one of these Nokias? Yep, you did? 1, 2, few? Good, I had them. So for the first time, electronics was so small that you could actually have it with you, and with that it became fashion. Right? So now it had choice of colors, just like that iMac here, the very first iMac that was created. But we weren't done yet, and we said let's go to 12-inch wafers. Let's use an even shorter wavelength. Now we're at a wavelength of 193 nanometers. And let's also make sure that that piece of equipment spends 100% of its time on printing wafers. So if I have a wafer that I need to work on, I place it on a wafer table. I can do that with an accuracy of mechanically 10, 20, 30 microns. But that next layer needs to land on top of it. The nanometer accuracy, right? So first I need to figure out how exactly did this wafer land on this wafer table. You do, and we measure alignment marks with that, with a laser. Then when the alignment is done, and I've also measured the whole height map, then I know how I need to expose it. I now move it here under the lens where the exposure happens. This wafer table moves back here. The old wafer that is exposed goes off. New wafer comes in. I repeat that I'm doing the alignment here while I'm doing the exposure here. We drive more and more productivity. No waiting to expose because first you need to do alignment. That's why we introduced dual stage technology. That altogether, larger wafers, much less wasted time, shorter wavelength, smaller features. We're now at, oh my gosh, we're now at 280 billion pixels per second. So now we got the iPhone, we got flat panel TVs, we got Game Boys and consoles, and we were still not done. So then we said, well, if we introduce a concept called holistic lithography, I'm going to measure from every wafer that comes out of the machine. I'm immediately going to put it into a measurement piece of equipment. I'm going to see what I really get. And if there's a small deviation, then I know how to adjust the schedule for the next wafer. So metrology and equipment creates control loops. Now, I don't have the time to look at 10 million transistors, whether they come out. So how can I select perhaps 10 structures that I can look at in metrology, infer from that what is happening with the 100 million or billion of transistors that are on my chip, and use that inference to say, this adjustment of the knobs make all of the patterns better. Because that's what customers were very worried about, right? You measure only a few patterns, you want to adjust them so that they're better. Are you going to mess up the rest of my chip? So being able to use that computation to make the link between what you measure probably means that this is going on with the process, has these consequences for all of the patterns that I have not measured. And therefore, now when I do my magic on the knobs on the scanner, it probably makes everything right. That was the concept of holistic lithography. And that drove us to the next level of, by now we're looking at 21 nanometer technology, 3.2, oh gosh, I'm starting to lose track of, 3.2 terapixels per second. And it keeps going. More powerful smartphones, more powerful robotics, etc. People start to sniff. We're getting close enough, and we have enough compute power that we can perhaps start getting serious about artificial intelligence and machine learning. Early 2010s, that was still a dream, but people started to sniff on it and think, we're getting close. Then we made a big step. We went from deep UV, which used excimer lasers, a wavelength of 193 nanometers. And you could still use that with quartz lens elements and refractive lenses. And we said, no, we need a shorter wavelength. And the next shorter wavelength was really, really tough. I have a whole course on that, EUV lithography. We went in one go from 193 to 13.5. Because there was nothing in between. And 13.5 was fantastic, really, really short, but it's tough to make it. That sort of light, very complex light source. The photons are also so energetic that everything absorbs it. Go ahead.
Why was that such a large jump?
The large jump was mostly because once we tried to go from 193 to 157, the photons already became energetic enough that they could start to do damage to any type of glass. And imagine this multi-million-dollar lens that you have becoming a consumable when you're producing chips. That's not going to work. So we were stuck at 193 nanometer for a long time because we were still working on refractive optical systems. And the only way out of that was to move to reflective optical systems. But at these short wavelengths, what is light? What is the light that you're going to use? And instead of an excimer laser, where it's a chemical reaction basically that creates the laser light. We now suddenly you use spontaneous emission. So you create a plasma. In this plasma, atoms collide violently with each other. They knock inner shell electrons out. And when an outer shell electron falls back to that inner shell, that energy difference is emitted as light. And that simply happens to be that big jump. There was nothing in between. But it came with a lot of complications on how do you create mirrors for these very short wavelengths, and the regular mirrors don't work anymore. We can talk much more about that. Yes? Yes, correct. Yeah. So what he's referring to is the fact that the refractive index determines, of course, in refractive systems how much breaking you get, right? But in reflective systems, when you get reflection on a layer, the amount of reflection that you get depends on the change in the refractive index. And I need to go for the refractive index itself depends on the wavelengths of the light that you use to look at. And very close, but for these very short wavelengths, nearly all materials have a refractive index that is a few hundredths away from 1. And on a scale of things, a good glass has a refractive index from 1.7 to some even over 2. High refractive index, you know, when you can't see very well but you still like your glasses to be thin, you use a high refractive index glass that has a refractive index of over 2. But at 13.5 nanometers, every layer that I try to use as a mirror, it will only reflect 1% of the light. So what we then do is we say, let's have one layer of molybdenum, one layer of silicon. The first layer reflects some light. Next one, that I have a silicon to molybdenum interface, I get 1%. Next one, I get 1%. If I make the thickness of all these layers exactly right, then this light, and this light, and this light, all has the same phase, because the path length every time changes by one wavelength. So it became really, how can we make these multi-layers with exactly the right thickness so that I get this reflection? And ultimately now we can achieve about 70% reflection. Yeah. So there is a lot more that I can tell. If you're interested, stay afterwards. We can talk a little bit more. I love to. And I'm going to go back to the rest of my story. All right? So now with EUV light, we're actually able to have 45 terapixels of information going through a scanner, being transferred from the blueprint to the wafer every second. And you can see also that the poor king would, for that square on his chessboard, he would have to fill 3 ocean tankers, each ridiculously long with rice. So you start to see the power of what is happening. This is what we were able to build with it, and now suddenly we're in the era of AI. So here you can see what has happened with the lithography so far. That's the backward-looking part of my presentation. Let's now pivot, turn around like a Janus, and look at what is going on going forward. And really AI, we've all heard that. The investments that people are making are incredible, right? It seems like the unit of money that is now being thrown around in AI is what? You know? It's about, I would say, $100 billion, right? That's the minimum that you need to put on the table to play. And data center investments of, no, I'm not going to spend $100 billion. I'm going to build a data center of $200 billion. Well, if you're going to build one of $200 billion, then I'm going to build one of $400 billion. Because I'm going to run faster than you. That's really the world that we now live in, right? So it drives the equipment industry tremendously. And AI is really everywhere. Here you see how societal changes, connectivity and so on, it has impact everywhere. And it drives a market value and generative AI. People really believe that this will add $6 to $13 trillion to the gross domestic product worldwide by 2030. Those are incredible numbers. And if the bounty is $13 trillion of value per year, then yeah, $600 billion investment suddenly doesn't sound like that much money, right? But in reality, it's an incredible amount of money. Now, a lot of that is also driven by all of you, because you become more and more impatient. You know, in my generation, some new technology, and 3 years later, somebody would buy it. And by, when WhatsApp in 2009, it took 49 months to get to 100 million users. And ChatGPT did that same thing in 2 months. So it's all of our appetite for technology that is driving this. Meanwhile, Moore's Law, we've just gone through 50, 60 years of doubling every 2 years, and we've seen how incredibly powerful that is. So doubling 2x every 2 years, that's incredibly powerful, right? Yeah, you know what? It's nothing. Because the appetite in AI is much steeper. No. The AI has an appetite that is going up by 16x every 2 years. And from the hardware that we're producing, we can only give you 2x. So we've got a problem. Well, then I'm simply going to buy more hardware. And that the hardware, luckily, is also getting a little bit more power efficient. So here you see a scale of power. Here you see a scale of compute. And to drive this compute, I need to buy so much hardware that guess what is happening with the power consumption? By the mid-2030s, unless we do something dramatic, 100% of the world energy consumption will be in data centers. That's obviously not going to happen, right? That's nonsense. So something needs to happen. Well, 4 things that I'm going to take you through. One is, and let me quickly check, how am I doing on time? 10 minutes? Okay, I have 15 minutes, I hear. The software guys are making the algorithms much more efficient. We're making the chips more efficient, and I'll talk about all 4. So more efficient training. How can we use models with more parameters, with larger data sets, and still spend less compute on training those models? That's really the game that is going on right now in AI. And we need the chips to be more efficient, and we do that with the transistor technology. We do that also by bringing memory and logic closer together, and I'll talk about all 4 of these. And ultimately, even the equipment that we use should be more energy efficient, because it's not just the energy that is used to use the chips, but it's also the energy that is used to produce the chips that matters. And just to give you a reference on that last point, one of these EUV scanners of ASML, with all the infrared power that you need to create this plasma that emits the 13.5 nanometer light, with accelerating wafer stages to get the productivity at 40G, 5 megawatts for one scanner. Can you imagine a factory with a bunch of these scanners? How many megawatts that is? TSMC is a large producer of chips in the US, in Taiwan, right? Anybody dare to make a guess? What fraction of the energy consumption in Taiwan is just for TSMC?
3%? 10%? 20%?
A little bit less than that. Just around 10%. Right? But isn't that one company, 10% of the energy consumption of a whole country. So we have to do something there too, right? That's that fourth point. Let's first look at the first one. Can we count on our software buddies and our algorithm buddies? So what I'm showing here, you can see it here at the bottom, the expected compute, I'm going to say if I have 10 times more parameters, I expect 10 times more computation. If I have 10 times more data and 10 times more parameters, I expect 100 times more if I just brute force it. And then we have the actual amount of compute. And I can take this ratio. And if the actual compute is much smaller than the expected compute, then I have something that is very efficient. So that's a high efficiency number. And I don't want it to blow up, so I take the log so that it becomes an exponential scale. That's what we're plotting here. And what you now see is that algorithmic efficiency compared to these early times that we started to smell AI could do something, and where we are now, and you see DeepSeek and ChatGPT-4, basically, our software buddies have been so smart that they're 1 billion times more efficient in training these new models. But, I'd like to see another factor of 1,000 out of them. Let's see what they can do. On the computer side, we also need to do stuff. We need to make the architectures of our compute more efficient. And here you see one way that people are doing that. In a modern data center that is doing training for AI, as much as 60% of all the energy is not to do computations. It's just to move the data from the memory to the logic chip where the computation is done, and then to move the results back. What if I could teach my memory chip to do some of the computation itself and only communicate the results of the computation to the CPU? Now, what operation would I want to teach my memory to do? Oh, whether I do a matrix multiplication, or whether I do tensor calculations, or Fourier transforms, or convolutions, or convolution neural networks. The basic operation is always take two large columns of data, multiply them with each other, and add it up together. Basically an inner product between two vectors. If I can just teach my memory to do that 60% of all the energy wasted on transferring the data, perhaps I can take 50% out of that and take it off the table. That really moves it. That's called processing in memory. Something that people are working on. We're now getting very close to seeing some experimental devices where that is possible. But from a processing technology, it's very complicated because the semiconductor manufacturing of memory is quite a bit different from logic. And now you're trying to mix the two in together. That requires much more precision. Oh, wait a minute, I have EUV scanners. There may be an opportunity to do some of that. Here you can see now what we're doing on the transistor side. And who has already taken any transistor class or knows anything about a transistor? But a transistor is basically a source of electrons, a drain where the electrons go to, a semiconductor here, and that one normally doesn't conduct. But if I put a little insulator here, a gate oxide, and a gate on top of it, the potential on this gate can attract some electrons, and then these electrons can start moving. So now I have conductivity. That was called a planar MOSFET, and we've had that for a long time. That's on this chart, that's further off to the left, further in the past. When I try to make that transistor smaller, a couple things happen. If I look at it from the side, and it's getting smaller and smaller, it gets harder and harder to turn off that transistor. I get more and more leakage current. So people said, what could I potentially do? You know what, if I take the transistor, and now imagine the source being here, the gate being here, the drain being here, the gate is on top, but the gate cannot control the conductivity here anymore. I get leakage current. What if I took this all up and just folded it up like this? So, drain here, source here, channel here, and the gate wraps all around. That is that FinFET. That's the basic idea. Then we said, but if I've now taken the width of the transistor, which defines the amount of current, and folded that up, so that's now basically the height of the fin. From a semiconductor technology perspective, when I had planar MOSFETs, it was simple to make a wider transistor that had more current. I just changed the layout. But now I can't do that. So if I need more current, I need more fins. Now, but that's going to take up more space. You know what? If having the gate on 3 sides of the channel is better than on 1 side, then 4 sides must be even better, right? So why don't I take this whole stack, move it over like this, and now I have a bunch of sheets like this that it needs control, that can each conduct electricity. That's the one that we have here now, these nano sheets. So what's going on here? Remember that simple Texas Instruments flip-flop device? And I said a flip-flop is a PMOS and an NMOS. So the one is standard on, and with the gate voltage it turns off, and the other one is the other way around. What if I could make a PMOS and an NMOS and put them right on top of each other? Then I could make a complete flip-flop in the location of just one transistor. And this one transistor, if I have enough of these sheets, it actually has a lot of drive current. So it can drive long lines, it can make the circuitry fast. And if I want even lower voltage, because we were also talking about power, we wanted the power to be lower, so I want all the voltages to be lower. If I have less the switching is something like V squared R, right? So if I can halve the voltage, I only need a quarter of the power. But then it becomes even more important to be able to turn it off, because now I have so little voltage change between the gate voltage being on or off. So that's when we say, can we make these nanosheets and these CFETs, can't we make them thinner? Well, what happens when I have this conducting sheet of material? And if we really look at it at a detailed level, an electron, by the electric field, gets accelerated and then scatters. And that acceleration, scattering leads to an average speed of these electrons, and that is called the mobility. You guys are going to learn that later on in some of the semiconductor classes, and that defines how much current you get. So if I can reduce the amount of scattering, then I get more current, right? That would be cool. So what we're now looking at is, can we actually make intrinsic 2D materials, like these graphene sheets, where electrons only move this way, and therefore they would only scatter here, instead of they move in all directions, and if I move it thin, there's always an interface close by, right? So a 3D material that gets very thin, the mobility suddenly collapses. Or at least that's the fear. There's also some new results that might not always be the case. So, in the interest of time, I'm going to skip forward a little bit. I do want to show you this. This is, in essence, the roadmap of ASML already for more than 30 years. Our value proposition to the industry is very simple. We try to make as many good printed transistors as possible for the lowest cost. And we do that by increasing the resolution, making sure that the yield is very good, that the overlay is very good, and by driving productivity. And then we try to reduce the number of these operational costs and power consumption. Let's look at the productivity. Here you can see what we have been able to accomplish with the availability of a scanner. These are extremely complicated systems. When we first started, you have just bought a $150 million scanner from us, and it works 60% of the time. And the other 40% of the time, we're fixing it. Are you going to be happy with me? No. So it's very important for us to drive that availability up. You can see now that worldwide we're at 93.5%. That's pretty amazing for complex technology. As a consequence, the number of wafers per day that we can process on one scanner is now approaching 3,000 wafers per day. That all goes into that productivity. In terms of the overlay, here you can see what we've been able to do. On 3,400 scanners, we can actually make sure that every layer lands on top of the previous layer within 1.5 nanometer accuracy. But now on the latest scanners, we're already at below 1 nanometer accuracy. And what is necessary for this is stunning in terms of the complexity, but multiplied by the trillions and trillions of transistors that you make, the value is incredible. If I can make the resolution even better, look here on the left. If I have a numerical aperture, that is how big is my lens, that drives the resolution. If that's limited to 0.33, and let's say I need to make a connection between this one and this one here, but there is also something going on here, then I basically first make these contacts. Then I can have metal run in one direction. I need another metal going in the other direction. So to get from here to here, I first need to go up. In another layer, I need to go there. Then I need to go down, sideways, back up, back to where I was, and back down. And each of these contacts is resistance and is process complexity. If I have better resolution, bingo, I can just do that. Here in the middle, you see what we're now able to do with High-NA in terms of the quality of the processing. And here I'm showing some results that are from late last year. You can see here that on the High-NA scanner, we can now print these contact holes that are every 28 nanometers, we have a contact hole. And numbers for a second. NVIDIA Blackwell chip. Right now, 200 billion transistors on one of those chips. I need a source, a drain, and a gate contact. I have 600 billion contacts. Takes us about 100 milliseconds to print all of those. And they all need to work. And while they are, now that's roughly here right now, but this is what we can already do. At a local CDU means that 99% of all the contact holes are the same size within a range of 2.3 nanometers. It requires ridiculously accurate mirrors. On the right-hand side, you see metrology at Zeiss, where they make the mirrors. That's just the vacuum that we need to measure with interferometers the accuracy of the surfaces. Since we're here at Purdue, if I have a very accurate mirror, I also need to aim it accurate, right? These mirrors are so accurate that they have about 20 picometers of surface accuracy over an area of 1 meter. That also means an aiming accuracy of about 20 picoradians. If I multiply 20 picoradians with the distance to the moon, which is about 384,000 kilometers, I come to the conclusion that if Neil still were up there and he were to dump a quarter, we would say, hey, do you want to, come on, why is that not? Come on, this is so cute if it works. Come on, come on. There we go. Yeah, we can choose to hit the left side or the right side of the quarter. Yes. Probably even one. So, lots more about this light source that we already talked a little bit about. Packaging. Now that people are going to more advanced packaging, even the substrate where all these packages are put on is becoming complex. Semiconductor technology, these are interposers. We're now launching a series of scanners where we can take very large interposers with semiconductor technology, and that means even more connectivity between memory and logic and more performance. So that's the technical end. Very quickly, ASML, here you can see where we're all present. These are some of our major locations, specialized in many, many areas. I want you guys to look at this because you come from a lot of different backgrounds. There is room for all of you, whether you're in industrial engineering, in chemical engineering, whether you like math, whether you like mechanical engineering, whether you're a physicist and you want to do plasma physics. We need everybody. You guys have a bright future ahead of you. Somewhere in that future, right now, these were originally developed as master's level classes. This fall, I've also opened it up to senior undergraduates. So when you're a little bit further in your education, hopefully I will see some of you back in my classes. And if you want to know something really cool, this was published in the last week on YouTube. It's about a 30-minute video. Highly recommend to watch it for everybody that is interested. I helped produce it together with many, many other people, and it's very educational. So highly recommend it. And I promised that I'd finish with showing my own LinkedIn account again. Thank you very much, and I'll be around for a little bit longer for questions.